Welcome to the University Utara Malaysia School of Computing. Today, we are covering Chapter 4 of Dr. Jabbar Al-Maliki's lecture series, Public Key Cryptography. In our previous chapters on symmetric encryption, we identified a primary vulnerability. If Alice and Bob want to communicate, they must use the same secret key. However, if they are communicating over an insecure public network, the act of sharing that key presents a point of failure. If an attacker intercepts the key during transmission, the entire system is compromised. Public key cryptography addresses this by using a pair of mathematically related keys. Bob makes his public key available to anyone who wants to send him a message. Alice uses this public key to encrypt her data. Once encrypted, the data can only be decrypted by Bob's private key, which he keeps secret. While this asymmetric process requires more computational power than symmetric systems, it eliminates the need to share a secret key beforehand. This function is what allows the modern internet to scale, providing the security framework for HTTPS, VPNs, and blockchain. To understand how these keys function, we have to look at modular arithmetic. It is often called clock arithmetic because it focuses on the remainder after division. If the current time is 10 o'clock and we add 5 hours, the clock loops back to 3. In mathematical terms, 15 mod 12 equals 3. Modern cryptography depends on the properties of prime numbers and modular exponentiation. For example, 3 to the 4th power is equal to 81. If we calculate 81 mod 5, the remainder is 1. This creates a one-way function known as the discrete logarithm problem. While it is computationally simple for a computer to find y if it knows the base, prime, and exponent, it is mathematically infeasible for that same computer to calculate the exponent x given only the result. We also use Euler's totient function, which we will need for RSA key generation. This function, denoted as phi of n, counts the numbers that are relatively prime to n. For two prime numbers p and q, the totient is simply p minus 1 multiplied by q minus 1. With 5 and 11, our result is 40. These one-way mathematical operations provide the computational security that protects asymmetric algorithms from an attacker. The first practical application of these principles was the Diffie-Hellman key exchange. Developed by Whitfield Diffie and Martin Hellman, this protocol lets two parties establish a shared secret over an insecure channel without sending the secret itself. Alice and Bob start with public parameters p and g. Alice uses her private value a to compute public a, while Bob uses his private b to compute public b. After exchanging these public values, they both perform a final modular exponentiation. Because of the mathematical properties involved, they both arrive at the exact same shared secret key. Diffie-Hellman is mathematically sound, but it lacks authentication. If an attacker intercepts the public values and replaces them with their own, they can perform a man-in-the-middle attack. To prevent this, the exchange must be paired with digital signatures to verify the user's identities. Taher El-Gamal later adapted this logic for encryption. Unlike a standard key exchange, El-Gamal encryption uses a random number k for every message. This produces a randomized ciphertext, meaning the same message will look different every time it's encrypted. Both Diffie-Hellman and El-Gamal remain secure as long as the discrete logarithm problem remains computationally difficult. While previous methods focus on logarithms, RSA, named for Revest, Shamir, and Adelman, is based on the difficulty of factoring the product of two large prime numbers. Let's use the tools we've discussed. Pause the video now and calculate n and the Euler totient using the prime numbers p equals 3 and q equals 11. For step 2, multiplying 3 and 11 gives us an n of 33. For step 3, the totient is 2 times 10, which is 20. If we choose a public exponent e of 3, we then compute the private key d such that 3 times d mod 20 equals 1. In this case, our private key d is 7. These values form the key pair. To encrypt a message, we raise it to the power of e modulo n. To decrypt, raise the resulting ciphertext to the power of the private key d modulo n. Because asymmetric encryption is computationally demanding, we typically use hybrid encryption systems. Protocols like HTTPS use RSA to securely exchange a one-time session key, and then use that key with a symmetric algorithm like AES for high-speed data transfer. RSA is a current security standard, but the development of quantum computing poses a specific risk. Because Shor's algorithm factors large integers efficiently, researchers are developing post-quantum cryptography to replace these methods. This table summarizes the core differences between the algorithms we have studied. Note the security basis for each. While RSA relies on integer factorization, Diffie-Hellman and El-Gamal rely on the discrete log problem. Use these exam notes and discussion questions to guide your self-study. Ensure you can explain the Diffie-Hellman exchange and perform the basic RSA calculations manually before our next session. Understanding these mathematical foundations is the necessary preparation for our next topics, digital signatures and the implementation of blockchain technology.